Are you able to see my screen?
Yes, sir.
So today we'll discuss about multi-threading. So last class, we discussed about multi-threading, but today mostly very brief of actually locking protocol, particularly locking things. Okay, so and what are the problem arises in threading? So that basically maybe in lighter node, most particularly locking protocol, locking things we'll look at. And then we'll move towards implicit multi-threading. So implicit multi-threading means we don't need to write actually multi-threaded code. So given a C code with nested for loop or for loop kind of simple structures, so give some input to the compiler so that compiler will generate automatically a multi-threaded code. Okay, so instead of writing multi-threaded code, so you give a compiler options and let's compiler generate the multi-threaded code automatically. And nowadays for this work, particularly OpenMP, okay, open multiprocessing. So that is more popular and very easy to do multi-threaded program using OpenMP. Okay, so given simple structure of C code, particularly simple array and nested arrays. Okay. So in this threading, so we'll discuss about basically thread safety, then thread synchronizations, the basic one. Then we'll go for implicit or auto thread pooling or auto threading. So we can write our manual code to do the threading, okay, or we can write manual code and we can assign work to the threads manually and do the things. But there are some tools, particularly OpenMP, which is actually part of GCC, and another thing is Silk, which can be used directly to write actually automated threading codes. Okay, so that is implicit threading code. So thread and memory model and safety will look at. So in particular means any threaded program. So threaded program is shared memory programming model. Okay, shared memory programming model, multiprocessor programming model. So whenever we are saying thread means shared memory programming model, the question is which variable in threaded C program are shared variables. Okay, so always it's not simple as global variables. In general, whenever you say global variables are shared and stack variable are private, and then for each thread who have their own program counter, register, all are particularly all stack variables and what I can say local variables are privates. Okay, and this is well known, but it is not clearly separated. Okay, so even stack variable also can be accessed by the other threads because uh, in a process we can create multiple threads, and inside a process, whatever may be the thread number, it can access the whole area of the means a whole what I can say memory area of the process. Okay, because OS will not bar from accessing each area. Okay, so it's the same process area, even if they are from different thread, but they can access through pointer or some kind of other things. We can access the things and require answer to the following questions: what is the memory model for threads and how variable are mapped to the memory instances? So based on this, actually, if you look at the process, for whole process, OS will allocate for the whole process. Okay, and OS will not interfere with the threads. Okay, so for in memory allocation term, so it will take it as a whole. So in that way, as any thread can access any area of that process. Okay, any thread memory area of that process. That means because whole memory model is shared. So this is a simple examples of threading. So that we have already seen this kind of things. So what in this code, what we are doing is this is a parallel counter without any log. Suppose we are not using log. So in this first case, so let me see the things. So this one, so let me change to pointer. it don't say arrow, it says only. I don't say larger point. Okay, it's fine. So we are creating two threads, P1 and P2. Okay, P1 and P2, and then in parallelly, what we are in parallel thread, what we are doing. So we are calling a functions count, where we are counting up to mensa. Initially, the counter is a shared variables. Count is equal to 0 initially, and with two threads, we are trying to count means add the counters. We are incrementing the count. Okay, and for each thread, we are incrementing up to 100. Okay, so in total, it should be 200. Counter should be final value should be 200 because in two parallel thread, we are trying to increment the counter 200 times. Okay, so per thread 100 times we are trying to increment. Because counter is shared variables, whenever you run this code after compilations, so actually we will not get 200. We get either less or more. Most probably we'll get the number is less. Okay. So why this happens? Because this counter is a shared variables, and both the threads, they are accessing the counter shared counter variables in writing mode. Both the threads accessing the shared counter variable writing mode. So that's why whenever any shared variables were accessing in writing mode, so we should do using lock, so that whatever in OS we read about critical sections. This is actually this counter increment is a critical section problem, and we need to handle through lock. And count should be 200, but what one time because of this it is not incremented properly, or it is not protected properly, not what you can say incremented in a proper way. That's why this count value is less. So because of that, because of things, we need to first lock, then only we should increment because it is shared variables. Is both the threads accessing the counter variable in write mode, incrementing the counter. And whenever we discuss about any threading model or threading things, then we should look at about thread safety. So thread safety means, so functions called from a thread must be thread safe. So what is the thread safe? That means ultimately means they should not interfere with each other. So are disturb with each other. And it should be done. So kind of in previous examples, we're supposed to do must increment 200 times because both the threads they're trying to increment the share variables. Instead of incrementing 200 times, it is incrementing 196 times or 184 times. Means it's less number of times. So that kind of interference we're seeing. Okay. So functions called from a thread must be thread safe, and there are four non-disjoint classes of thread unsafe functions. Okay, so first one is failing to protect the shared variables. Previous examples. So we should do lock, unlock, then only we should increment the shared variables. Second class is relying on persistent state across invocations. We'll have examples for this. Then returning pointer to a static variables. Okay. Then calling thread unsafe functions. These are the four classes. Let's discuss one after another. One on examples maybe. In class one, so previous examples, we should lock the shared variable count. So this one is fix. How to fix these things? Use log and unlock semaphore operations. Issue synchronizations operations will slow down the code. So whenever you fix the code, because both the threads are trying to access the shared variable count, and whenever you lock the things, that means only one guy can access. That means it will create a queue. And whenever you're creating queues, that means it will slow down the code. And good example of this same code is previous example code is actually, so before accessing the log variables, we should first log the variables. This is the locking the variables. This one is pthread mutex lock. This is lock variable is LV, and increment the counter, then you release the lock, unlock the log variables. So where LV is log variables. So before increment, you lock the log variables, and after an increment, you unlock the log variables. So in this way, it will be synchronized. Synchronized means the shared variables will be accessed by one thread at a time. Second example, second things, not second class of what I can say, second class of threaded onset functions. So relying on persistent state across multiple function invocations. Suppose many threads trying to access these functions, particularly functions. This is one example. The random number generator relies on static state. So this particularly whenever we declare the static, every time I need to change to pen. So this static unsigned in next one. Whenever you declare static variables, so static variables for all function invocations. So this is fixed. Okay, so this is one variable get created. Okay, static unsigned in uint next one is equal to this means this one will be created for all invocations of the rand functions. Only one variable space will be created. That means for all invocations, suppose you are invoking these functions from multiple threads, then for all multiple threads, that means they will rely on only one variable space. Okay, so that means one memory locations. So how to fix that thing? So rewrite the function so that caller passes in all necessary states. Okay, so maintain thread specific states, or you write for one thread, this is the rand functions, another thread, this is rand2 functions, maybe. So in that way, you can separate the things. Third case.
Sir, can you explain it again?
Sir, in the second case, what is the problem with the code? Could you explain it again?
So this is persistent state across multiple invocations. Suppose from different thread who are trying to invoke the functions, this rand functions. Suppose you are trying to invoke the rand functions. This rand functions from different threads. Okay, because the function is one functions, but we are invoking from different threads multiple times. Different threads. The static variables in the functions, it will create only one space, one variable space. This is not, it will not go to stack. Whenever you declare static variables inside functions, so it will go to different memory locations. And for all invocations, this memory locations, that address space is same. That means you will have only one variables. And whenever many threads try to access these functions or call these rand functions, they will see the common space.
So, excuse me, what if we don't use this static keyword and declare next directly in the function itself, and then use mutex logs or something? Then
look at if you read a code of random functions. Okay, so every time whenever call rand functions, it takes the previous state and get the next number. If you don't do this thing, then that will not get reflected. That is not the mensa proper random functions.
oh, okay, sir. So the next state depends on previous state, so we have to declare global. Is that the case?
That is a random functions in C language. It default it do like this.
Okay, thank you.
And third type of this thing is actually third class. It's returning pointer to static variables. So again, same thing. So if you look at, so let me change the point. So in this case also, if you look at the same thing is happening. Static start post net edge. This edge variables is actually static variables. For static variables, what happens? It creates only one memory locations for many invocations. Okay, so in this case, rewrite the code. So color passes pointer to the struct issues and require change in color and curly code. What is the fix? So because in this case, if you are using for modifying purpose or reading purpose, so that's fine. So first of all, you log the things, the edge variables, and copy all the things to own memory space and do the things. And make memory must be free after that. So how the fix what we are trying to write. So in this case, for every memory, for every invocations, this is the fixed one. So for every invocations, so this is we're getting host name, and this one is we're getting queue. Okay, so for every invocations, we are creating a new memory locations, and we are copying the whatever the things data of this place to new memory locations and returning queue. So even if this is static variables, new extra variable is getting created. So in this way we can.
So please repeat this with the problem again.
So whenever you are share the static variables of functions among threads, then every invocations, because static variables have actually one locations. Whenever you use static variables, the property of static variables is it will this OS will give only one memory locations for all invocations. For all invocations, the variable h will get single locations.
Sir,
Same
uh,
or multiple threads.
if 10 functions invoke this function, then each of those 10 host and edge will be same. So there can be data corruption.
Yeah.
Okay.
Because this h will be shared by among all because it is static. Suppose 10 threads, they invoke this by name function. That means for all 10 threads, the h variable will be same because of it is static. So ultimately, it's boiled down to actually sharing variables or sharing data. And what kind of sharing may happen, that we are looking at. Okay. And how to fix that. So in this case, for everything, Q will be shared. Okay. So because in this case, Q will not be shared because every time we are allocating a new locations and returning that location. Okay. So every time we're creating a new locations and getting that locations. And whatever we wanted the requested thing, we're copying back into Q, and for each invocations, we're returning new locations, new variables. So it will not be same. It will be different.
Hello, sir.
Yeah.
Sir, in the class 2 and class 3, in both the classes, we are making the static variables.
Yeah.
So then what's the difference in these two?
So one thing is using static variables, persistences. Other thing is returning the static variables, pointer to static variables. So one thing, so using the static variables, relying on persistent state. And another thing is returning pointer to the static variables. Returning pointer to the static variables means in other functions, this caller may use these locations. Is clear?
Yes, sir.
In first case, yeah. And fourth case is calling thread shape functions. So what is thread shape functions we'll discuss. So calling one thread on shape functions make the entire function thread on shape.
Excuse me, sir.
Ah.
Excuse me, sir. Sir, in the previous class, if instead of returning the pointer to static function, we copied the static function and then returned it by using the
So
lock, like in class 1.
Yeah, here address space gets changed. So
Like
equal to value.
So then it won't remain a shared variable, right? Because each callee function will change the address space.
Yeah, but whatever you are getting, p is equal to get by hostname. That thing is getting copied to a new variables queue, new locations queue, and we are returning new locations queue.
So each function will return new location.
New locations. Create new locations and return new locations.
So then what is the use of creating this thing static?
Look at. So in sometimes we may write code like this. if you write code like this, then this will interfere with each other. So we want to remove the interference.
In this case only, if we instead of returning the address of H, we copied it to another pointer and then returned that, then it would have been same, right?
We copied and then return, and then we are modifying. Or in this case, the queue is separate for each calling.
Okay.
Whenever it is calling from different thread, it will be different.
Excuse me, sir. So in the solution for this class 3 problems, we are not using static variables whatsoever, right? I mean, there is no static variable. We are just copying a pointer and returning a pointer so that.
Yeah. P get host name. If you look at P get host name, we are doing that. So in this case, the function is get host name.
Yeah.
Okay. Function is get host name. Get host name using actually static variable. But we are get host name, we are making another functions which is thread safe. We are not returning the static variables, but what we are trying to get the only copying the data only.
Okay.
And then we are modifying whatever we are trying.
So we have just enveloped the old function by locks. No?
Yeah.
Okay.
Not lock. So yeah, lock, and then we are returning the new locations.
Okay, sir.
So it will not interfere. So it is a thread safe functions. Okay. So that's why I get host name thread safe underscore ts. Or sometimes thread safe people write, and sometimes people write r underscore r, that is reentrant. Okay. So calling one thread onset functions make an entire functions thread onset. And how to fix? So fix is modify the function so that it call only thread safe functions. And let's see many examples. So a function is reentrant. So either sometimes we call actually thread safe or reentrant, but reentrant is more what I can say formally defined. So a function is reentrant if and only if it accesses no shared variables when called from multiple threads. That is called reentrant. Okay, so it is more stricter way of defining. And reentrant functions are proper subset of all thread safe functions. So you can see in this figure. So in this figure, you can see this reentrant function are subset of thread safe functions. Okay. So reentrant functions even only it access no shared variables when called from multiple threads. And whenever you looked at any library functions, particularly malloc, free, printf, scanf, most functions in the standard C library, backup your means whatever Canon G textbook, all are thread safe functions. You can call from multiple threads. So they have written in this such a way that it is thread safe functions. And all Unix system call are thread safe functions. And many library functions that are not thread safe, this is sc times, c times, then get host by address, and for that reentrant functions also they have created. Okay, so if you go to the library, so we have actually reentrant version also. That means thread safe versions. We can get actually underscore r versions so that it will be thread safe. Okay, and why thread safe is necessary? Because whenever we're writing multi-threaded program, so it should be thread safe. Once it should not interference should be as minimal as possible in particular data race conditions. Okay, and for thread safe, so in general, first whatever any shared variable I'll try to lock. Okay, any accessing to share variables or share space or maybe share file. So we try to lock, and whenever many threads try to access a shared variables, then ultimately what happens?
Race condition.
Yeah, race conditions. Ultimately, everyone in this case, this all the threads, this thread, and many threads, they're trying to access the this this is the shared variable. This one is shared resources, we can say, and through lock they need to access the shared variables or shared space, and then after accessing, they release the lock. Okay, and ultimately means if there are a lot of share variable access, that means there will be a lot of critical section, and this part of code is serial access, because at a time one guy can enter. That means Even if you are using multiple threads, so this part will be serialized. Critical section part will be serialized. Ultimately, critical section part will be serialized. Even if you are in the multiple threads, this critical section part or shared variable part will be serialized. And for synchronizations, we have pthread mutex unit in simple C. So we have this pthread mutex mutual exclusion init, then mutex log, then mutex onlog, and there is another function. They have actually mutex trilog also there. So what is trilog? One thing is the initializations, then log, onlog, and trilog. So these are the 4 basic functions mostly you will use. Initializations means initialize mutex variable with means 0, then log and onlog. The log is for logging, onlog is for unlocking, and there is another thing is trilog. So can someone say what is trilog?
Checking if the lock is free or not.
Yeah, checking log is free or not. If the log is already logged, then where to wait? So trilog, if it is free, then only means log. Otherwise, don't wait. Do something else. Okay, or yield to some other threads. And whenever we're doing locking, so the serializations point, minimize the size of the critical sections. We need to be very careful. So rather than waiting, so check if log is available using pthread mutex trilog. If already locked, we'll return ebg and sometimes we may require to do restructuring of code. So suspend self by a thread yield or give chances to other threads. Okay, or suppose we have some other things to do, then you can do other things, and after some time you just again do the trial. So it's similar to whenever you are going to bank. Okay, so if you see this queue is very big, then what you will do? If queue is small, then you wait there. Otherwise, if queue is big, then what do we do? So we generally come back, and after some time we try. So we can tell you same thing, same philosophy. And this is the standard performance of locking people check. So if you spend or busy wait, it will waste your time. Suppose you go to bank and bank all queue are full, and if you want to do every work on that moment, then what will happen? So you need to wait there. Okay, then in waiting you will spend a lot of time. Instead, so you come back and after some time you go and do your work. If most probably bank will be free after some time, maybe. If that thing happens, then again you will wait. And this waiting period, so initially you wait for 1 time, then 2 times, then 4 times, then 8 times, exponentially increase the backup time. If many people are trying to access the shared variables, suppose 128 threads, they are trying to access the shared variables. Okay, suppose 128 thread, there is a suppose shared variables count. So earlier code, whatever I've shown, 2 threads, they are trying to access a shared variable count. Suppose instead of 2 threads, suppose there are 128 threads, they are trying to access the count variables and they are trying to increment the count. Then there will be a huge competitions to increase the count. So in that case, it's better to give way to others if they are trying to.
Sir, what is attempt like wait k amount of time for the first time?
So initially, you can start with actually attempt. Initially, you can start with one amount, so some constant amount. Then if you are not getting, then you increase twice, thrice kind of thing. So that is called exponential backup. So have you ever heard about this MAC protocol, CSMA protocol, carrier sense multiple access?
Yes, sir.
So in carrier sense multiple access also they do exactly same thing. So they sense the carrier. If carrier is busy, they will not send the packet. They'll wait for some time and then again they will sense.
How
Excuse
do
me.
we ensure mutual exclusion here?
Yeah, it is mutual exclusion. When carrier sense multiple access also, that is also CSMA also it is actually in MAC protocol because there will be one shared medium. At a time only one person can send. So here also, if you have suppose one critical section problem, one shared variable is there and many threads trying to access. Problem is same.
Excuse
It is
me,
different.
sir. In the continuous lock, the thread is getting CPU time and it's wasting CPU time there.
Yeah, wasting CPU time.
So what happens in back of lock? It does not get CPU time or what?
No, he will not waste in time waiting. He will do some extra other work. And also, whenever it go and try the lock, so at that time means CPU get time wasted, unnecessarily trying. So there are two. Whenever you go to bank, and suppose the bank queue is very big, and you are eagerly do the times on that day or on that time, then what will happen? You are increasing the queue. Also, you are acquiring another chair, and you are wasting time. If some other valuable work is there, you could have done that thing, but you are simply wasting and waiting. Three things you are doing: increasing
What
queue,
the valuable work my
waiting.
thread is doing? Isn't it a single processor system or?
No, it will be multiple processor system also.
Okay.
Even in multiple, that thing happened. So I gave very once what I can say real life example of bank. Well, same thing, nothing else. Okay. So next, the same thing. So performance of locking. Have you used monitor in your OS course? The same thing people use. Spinning or busy wait simply waste time. So there should be a method for queuing the shared accessor, calling the next guy when one guy finishes his work. Okay, so this is the standard monitor do. So best example or what I can say, layman example or common example is barbershop. You book the barbershop through phone, okay, and you get a call just sometime before your turn. Is this easy? Much easier. So monitor don't do means other than this. So he will register who want to access the shared variables and keep a queue, and he will call the next guy. So monitor is nothing but actually it's a kind of organized way. So no one wastes their time. And sometimes what happens if one process is holding the shared data, once he exit, then he will call the next guy. He will wake up the next guy. It is fine. Okay.
Yes, sir.
Yeah. So what are the locking in data structure? Have you read data structure course locking of shared data? Suppose you try to design a list, queue, or stack, and you want to implement your linked list or stack or queue that should be thread safe. So how you can design a data structure which is thread safe? Suppose you want to design a linked list or list, and you want to make the list to be thread safe. So locking the entire list for one thread to access, then it will not be a good one. So okay, you can go for fine level of locking. So let's see. There is a one particular area of topic of actually data structure that is called concurrent data structure. Concurrent data structure means multiple threads trying to access a data structure. How to make it thread safe? So there is a CDS list. Not CSE. It is my mistake. CSE stack. No, this is CDS stack. Then CDS queue. Then CDS priority queue. CDS hash. Then CDS heap. There are all list, stack, queue, priority queue, hash. All need to be concurrent versions or thread safe versions. Then only you can use them in our multi-threaded program. So general list stack queue we cannot use in multi-threaded program. Simply we cannot use. So given a bank with 10 to the power 6 account, suppose it is not ought to lock the whole database of the bank for one transactions. Okay, so the bank database may be maintained by a list or hash. Suppose a person A transfer money to another person B, or from account A money get transferred to account B. it is preferred to lock A and B to do the transactions. You lock A and B, so A minus balance X, suppose X amount of money you have to transfer, and then from A to B, so B dot balance plus X. We want to do this two write operations, A dot balance write operations and B dot balance write operations. Two things we want to do the transaction. One transaction is two write operations. These two write operations we want to do in a transactions, and we want to lock only A and B simultaneously and do the transactions, not the whole 10 to the 6 account lock all the things and do the transactions. Fine grained transaction is much more preferable. Okay, fine grained locking is preferable. Okay, so there is a book called C++ in Actions by Melensky, and another book is Art of Multiprocessor Programming by Nils Sabith and Maurice Risley. So this Maurice Hartley got the Gödel Prize winner. So he designed actually very good memory model, actually very good concurrent memory model, and they have kept the concept of actually wait free and lock free data structures. So instead of locking, fine grained locking also, it can be further refined. Instead of fine, we can say more refined. Instead of lock on lock, we can go for lower level protocol of lock on lock. So even if you look at lock on lock also use lower level protocol. So why not to use lower level protocol to give performance to the locking? So there is a concept of wait free and lock free data structures. If you want to go and read more about this wait free and lock free, please refer this C++ in Action book or Art of Multiprocessor Programming. So I recommend this Art of Multiprocessor Programming, but this is a Java version of thing, but concept wise both are same. Okay. But in this course, we are not going to cover anything from this thing. Okay. And these are the basic primitive. So synchronization primitive, pthread mutex, init lock, unlock and try lock. And for maintaining the monitor, so particularly when OS monitor that thing. So we require another thing is conditional variables. There is condition wait, signal, broadcast, and init. And already this thing is discussed in our OS course. So we are not going to discuss about condition variables. So what is conditional value and this thing? This is simply I took from OS book itself. So no need to discuss this thing. What is condition variable and other things. And now let's discuss this thing. So this is actually our main things. So in wait free and lock free data structures, so they go to the further lower level. So if you look at all the synchronization hierarchy, let me change to pen so that it will be good. Yeah, yes. So this synchronization hierarchy, one used by other. So one used by other means, so internally all processor, so they use LL plus SC. So LL plus, what is LL plus SC? LL is load, link, and store conditional. So this is a lower level construct, and this lower level construct get used by all little bit of intermediate level construct. These are instruction level construct, that is called TS, test and set, compare and set, fetch and increment, and exchange. So in OS course, these are the atomic instructions: TS, CS, FAI, and exchange. These are the atomic instructions. And if a processor don't support atomic instructions, then we cannot implement locking and unlocking protocol. So that we know from the OS course. So have you heard about this TS, test and set, compare and set? Hello, student.
Sir.
Yeah.
Yes,
so
sir.
Yes, sir.
one of the instructions, this atomic instruction need to be supported by processor, that means architecture, to support lock unlock protocol. Otherwise, this is not possible. Okay, so either TS, CS, TS means test and set, then CS is compare and set, fetch and increment, exchange. These are the 4-5 basically people use atomic instructions. Okay, and the processor support this atomic instruction and OS use this. And sometimes if Java thread model. So Java thread model, they support atomic functions. Have you heard about in Java? Anyone have experience in Java? Have you used synchronized functions? Anyone who have used Java?
Yes, sir.
Yes, sir.
Yes,
So
sir.
what the synchronized function do? Synchronized functions. What is synchronized? Java synchronized function.
It doesn't allow two threads to access the same variable.
Yeah, not same variable, same functions itself. Java synchronized functions. Two threads, Java threads cannot execute the synchronized functions at the same time. So in Java, it supports synchronized functions, also synchronized variables. Okay, so but in processor, so if you want to simulate, so suppose your processor is not supporting this instruction, still you can simulate the locking unlocking by installing the software level of simulating the TSCS by using synchronized functions or synchronized data. Okay, that is software implementation of transactional memory that we call software implementation of transactional memory. So this guy, so whatever I told this guy, this Godel Prize winner, Maurice Hirsley, he got the Godel Prize. It is similar to a Turing Award or kind of a Nobel Prize kind of thing, second level to Nobel Prize. He got the Nobel Prize because of this software implementation of transactional memory. Okay, and if you look at other things, so lock unlock used by, so this log and unlock. So LLLC used by this thing. Okay, then this TSCS used by log unlock used by mutex. Okay, mutex is a little bit high level compared to log unlock, and then mutex is used by semaphore used wait and signals, and semaphore used by monitor. So ultimately monitor use the lower level LLLC or TS. Okay, this is the basic in OS course. You must have read these things. Okay, so we're not going in detail of this, but this is the synchronizations hierarchy. And log variable in multi-thread apps. So log variable LB in a single core machines, it looks fine. But in multi-threaded app, by default, we run multi-threaded app on multi-core machines. So log variables in single core machines, it looks fine. So try to run multi-threaded applications on single processor. Okay, single machines processor. It looks fine, single core machines. But whenever you write multi-thread code, most of the earlier days, what used to happen? So we used to simulate multiprocessing on single core. So at that time, it has log variables was not very difficult. But modern days, we run multi-threaded code on multi-core, and every core have private cache available on multi-cores. Okay, every core have private cache, and if the log variables, can the log variable be cached? First thing, because log variable is, it should be at one place and there should be at one transitional memory, transitional system. But now in multi-threaded core, okay, multi-core. So multiple threads are running on multi-core, and this every core have private cache. So another question is, can the log variable be cached? Yeah, log variable will be at private cache at different core, but we need to maintain the consistency. So working of log variable require atomic transitions. If consistency is not maintained at the private level of all the cores, then we cannot do the work. So for that, what the hardware level, what it ensures. So answer to the problem is the cache coherence protocol, particularly cache coherence problem or cache coherence protocol is responsible to maintain the state of the log variables. It maintains the consistency. That means now log variable can be cached, and this cache coherence protocol will maintain the state of the log variables. So nowadays in multi-threaded core, a multi-thread application on multi-core, particularly cache coherence problem is very much essential to implement very much essential to implement cache coherence protocol in hardware. So that's all multi-core processor. They implement very good cache coherence protocol to support locking. Is this clear? What is coherence? So I told you in the first class, coherence means at all the places data value should be same. Non-coherent means suppose one guy change, other guys should invalidate immediately. Okay, so coherent means the shared data should be same at all the places. Is this fine?
Yes, sir.
Okay. And in C++, so as this is C++ thread, not the C threads. So C++ thread, it's about C++ 11 and 14. So in C++ 11 and 14, so it support one kind of variables. It support one kind of variables. So this is called atomic uint. So this kind of variables, atomic uint. Atomic uint means at a given time, only one thread can access these variables. So in C++ 11, so we have this kind of variables, just like Java synchronized variables. So C++ have also similar kind of things in C++. C++ 11 and 14 since not the I have not seen the newer things. And the same thing you can do. This is shared variable. Suppose this is atomic count is shared variables, and many thread can access the variables, shared variables, and automatically it does synchronizations. Okay, and this is actually improved versions. Improved version means it first locally do the things, locally increment the things, and then after that it add the local counts. So if you look at this will be serialized code. This will be serialized code. For n threads, suppose n is 10 and every 10 threads they are trying to increment the count. Then for atomic count will be very busy because it required to do all the locking protocols. So for each thread, I need to be queue and only to allow only one thread to increment. But this code is improved code. The same work we are doing with improved code. So what we are trying to do, we are trying to increment the local count. Then whenever you are trying to add the local count, at that time we are locking and then adding. This will be a much more improved one in terms of performance. Is this clear? Any doubt about this? Hello?
So atomic count, like in its definition, uses lock unlock.
Yeah. So by default, this variable is synchronized variable. Only one thread can access at a time. Write access at a time. This is synchronized. Java synchronized variable. It is same as Java synchronized variable. Okay, so next we'll move towards another things that is called OpenMP. And OpenMP is a compiler directive, automatic license. It generates the threaded code and gets synchronized automatically. Okay, so let's see the what is we need to include OpenMP.h. And suppose there is a for loop for I is equal to 0 to n, ai is equal to pi plus ci, and we know. Suppose we know this code inside the for loop is independent code for each iterations. Okay, for each I, this code can be run in parallel. So suppose you know, then simply use this pragma. So this is compiler directive. We are giving information to compiler. Please try to parallelize it. Okay, so no need to write the multi-threaded code. So given a very simplistic C code, okay, C or C++ code, just give the compiler directives and this compiler will try to parallelize things. Okay, automatically generate. This is called implicit parallelisms, who are not writing explicitly. So this is implicit parallelisms, who are giving compiler directive and compiler is taking care of doing the parallelisms. So how to compile? GCC minus app OpenMP test.c, and then at the time of running, you need to use these variables. This is cell variables. OMP underscore num underscore thread is equal to 4. So this 4 can be increased to any numbers. Okay. So 2, 3, 5, 8 based on your choice, based on your number of what you can say processor or quality of processor in your system, and then run it out. So immediately you'll get that thing. So suppose I have this thing or not. Let me see. Okay, so there is a simple code I am writing. So back there. So this same thing. So similar kind of things is there. For this code, what this is very test code. So where pragma OMP parallel shared ABCD private I, then pragma OMP sections no wait. These are very compiler directive we are giving, and we are trying to parallelize this code. Okay, so this is the first slide. That's a saying it's very simplistic one. And how to compile this code? So this is it. Are you able to see the code? Compilations command. So GCC minus app OpenMP minus O, then compile vectorwrite.c, then lm minus lp thread we are doing. And then what we need to do? So we need to export. I think so. I have written all the things. So what I try to do, export OMP num thread is equal to 4. Then time run back.dad we run. So just run the executables. But in this case, you may not differentiate the time. But for some code, suppose matrix multiplication code or some bigger code, if you run for things, then you can see the difference between parallel code and serial code. Because in this code, we are not getting any difference. Almost parallel code is taking more time. Okay, so that may happen. So this is serial code. Okay, and this one is semi-manual parallelism. So pragma OMP parallel, and inside the this OpenMP block, what we are trying to do. So ID is equal to get thread ID, and what is the total number of thread? And total number of thread is actually environment variables. Okay, OMP num thread is environment variables we set in the bash or C cell, and then this is in start and end, just like in general pthread program how you are used to do. And then okay, what is this? We're not able to see code, so something happened. So now I can see the code, I think so. So this is manual parallel. So we're trying to extract the parallelism manually. So earlier case it was automatic. Okay, so this is manual extracting the parallelism. So we're from the thread ID and total number of threads, we are trying to get the starting locations and end locations. Okay, in which area this thread ID number thread will work. Not on the whole men's array. Okay, but in the portion allocated persons it will work. And we're calculating the allocated persons inside the OpenMP block. This is the OpenMP block.
So here the number of threads we will declare while running it.
During the whenever you are these things, so export OMP num threads were in this is cell environment variables. either C cell or base cell. In environment variable, we actually set the variables, number of threads.
So get number of threads will return this number and IDs of thread, right?
Yeah. So ID is for individual threads and OMP num threads, there's the total number of threads.
Yes, sir.
So get thread numbers is ID of self threads and OMP get number of the total number of threads.
Sir, how are we getting values of I start and I end?
So I start and I end. So this one is so suppose you are creating 4 threads. So every thread will get one numbers from this 0, 1, 2, 3. And n thread will be for all threads, the OMP number of thread will be 4. And for each thread, this I start and I end will be get calculated.
Okay, sir. So we are manually dividing the
Manually dividing the
iterations in n. Okay. Okay.
Yeah. This is manually divided. Earlier, whatever I used to do in general thread program, P thread program.
So what is the advantage of doing manually?
Manually, you'll get to know what's happening and you are assigning the work. That's the only benefit. But you can do automatically. So this is auto parallel loop. So pragma OMP parallel. So pragma OMP parallel lies the for loop with static scheduling. Static scheduling means suppose you have n is equal to 1000 and you have we want to run per 4 threads. Then it will statically divide into 4. The chunk size is 2 assigned to thread 1, chunk 2 assigned to thread 2, and chunk 3 assigned to thread 3. Simply it will do. So here you are doing manually, you are doing, it will automatically do the static scheduling, auto parallel for loop. So OMP have this flexibility we can do automatically. Okay, and internally whenever you do this thing, so pragma OMP parallel whenever you do, so for I is equal to 1 to 13, and suppose number of thread is 13, then for 1, 2, 3, 4, it will assign to thread 1, 5, 6, 7, 8 assign to thread 2, and 9, 10, 11, 12 assign to thread 3. So 1, 2, 3 threads get assigned 4 each. And this is the forking. Forking means creating a new threads. And this is implicit barrier, automatically get created barrier, automatically join the things. So in earlier case, so in simple p thread case, so we used to create thread and join threads. But here it is doing automatically. Threads are assigned an independent set of iterations. Thread must wait at the end of work sharing construct. And this is called work sharing construct. And not only this, for one loop, we can do for multiple loops also. So suppose for n is equal to 1000, this is one loop, then n is equal to 500, this is another loop we are doing. And this can be done in this way. This is serial sections, this is parallel sections, serial sections, parallel sections. Is this clear?
So, sir, we are explicitly saying that parallelize this for loop using pragma OpenMP parallel for.
Not explicitly. So we are doing implicitly, automatically. System is parallelizing. Implicit means automatically it getting done. Explicitly means we are writing the code for paralleling. Just like pthread join, pthread create, and pthread join, we write the code. But here we are not writing the parallel code explicitly. We are giving the compiler directive, and implicitly it is doing the parallelism internally.
Sir, will it necessarily do the parallelism implicitly, or it is dependent whether the loops are dependent on each other or not?
So whenever you say, so whenever you give compilations app OpenMP, then it will implicitly it will parallelize. Okay, and at runtime it will take the number of threads. How many number of thread it will create? It will take at runtime. So this slides. Let me show the slides. These slides. So this is the compilations. This one is compilations. And at runtime, you are setting the how many number of thread you are running in the environment variable. And at the runtime, it will take this value. You are compiling differently. And at the time runtime, it will take the number of threads based on the environment variables. Is this clear? Hello?
Yes, sir.
Yes, sir.
Sir, we
Okay.
can use this OMP method for loops or any other sections of code also.
Mostly it is used for loop. So it is mostly used for loop. But we'll have 2-3 more examples, and I'll give you reference where actually a lot of codes are given in OpenMP. Okay, many examples, 10 to 15 examples, even graph example also it is given in OpenMP. Okay, the extra examples or some examples, matrix-based examples. So I'll give the reference. Okay. So next class, I'll have 2-3 slides still remaining, but next class we'll cover that rest of the things. OpenMP. Then we'll move towards MPI. Okay, thank you. So if you have any other questions, let me know.
So when is the first quiz?
So after 10th class, so this course adjustment is still going on up to 26. They have extended the deadline. So in the next week we have the first quiz. So after 10th class. So we have total 40 classes. So first 10 class, after 10th class we'll have quiz, and it will be pre-announced quiz. It will not be a what I can say surprise. It will be pre-announced quiz. So I'll announce the date, means date and time within 1 or 2 days. Okay, so next week we'll have quiz.
Sir, can you explain static scheduling once again? Static scheduling.
Static scheduling, let me go forward a little bit. Okay, so this is the static scheduling. So suppose there are 10,000 iterations and 4 MP threads, and static schedule will chunk 10. So if you don't specify any chunk, this 10 is chunk, then what it will do? So it will take a maximum chunk. So 1000 divided by 4. So it will be how much? So 250, 250. By default, it will do like this. So 1000 divided 4. So 250, 250, it will divide into 4 parts, and each part will give to 0 to 250 give to thread 0, 252 to 500 it will give to thread 1, then 500 to 750 will give to thread 2, and then 750 to 2000 it will give to thread 3. Loop is get partition. Is this clear?
Yes, sir.
So we'll discuss in the next class one more time. So this particularly OpenMP things. So it will not take more than 10 minutes in the next class. Okay, thank you.